Um, Good morning, everyone. My name is Brandon Gwenya, and I'll be talking about buffer overflow exploits. I'm just going to share my screen quickly. Cool. So, what are buffers? Buffers are basically memory storage regions that temporarily hold data while it is being transferred from one storage location to another. So basically, an example would be if you're reading data from a text file, right? And then you want to read, let's say, 50 characters at a time. So when the program reads the 50 characters, it will store that data into a buffer until it reads the entire thing and stores it into the destination data type, right? So when a system writes more data to a buffer than it can hold, a buffer overflow occurs. And this has very different outcomes, and it can be very unpredictable. So when the overflow happens, the system can overwrite adjacent memory addresses. It can also overwrite various different other stack buffers that should not be touched. So the results can be very unpredictable, and it can crash the whole system. CERT did a audit of all the different vulnerabilities that have been reported, and about 50% of them have been buffer overflows. So they're pretty basic, but they can be very malicious. So let's take a look at what a basic vulnerability would look like. So basically, in the first example, you see the user is getting data from a file or from the standard input, but the buffer gets given a fixed size. So when the user gets the value, they don't validate the amount of data that gets given in by the user. So if your buff size is about 50 characters and then the user gives you 100 characters, that is going to cause a buffer overflow, and it's going to overwrite other different values in your system. The second one is also pretty similar. You have a buffer with a fixed size, but there is no validation when the data gets copied from one variable to another. So if the destination variable has a smaller size than the source, a buffer overflow can happen, and data can get seriously affected. So now that we know what buffers are, buffer overflows are, and what they look like, we can get down to some of the important things that you should know in order to spot when a buffer overflow happens. So the assembly language is an important part of programming. So when programs get compiled, they get compiled into assembly language, which is a very basic programming language that communicates with the computer. Assembly language is so basic that it is architecture specific. So if you're using an Intel processor, you can't use the same code. For example, if you're using a Raspberry Pi, and you can't use the same piece of code if you're using a Mac or something that uses a different architecture. So assembly basically, it taps directly into the system registers, which are the fastest kind of memory available in the machine, which are found deep inside the CPU. The CPU, the 64-bit CPU, which is the one that I'll be talking mostly about, and also the 32-bit, uses 16 general registers, the RAX, RBX, RCX, and all the others. These are very important because these are the registers that get used for most of the operations that you do. So if you're doing addition, or if you're calling a function and the function returns something, all that data gets stored in registers. Assembly doesn't use any variables. And another important thing is that since assembly doesn't use variables and it uses registers, there has to be a specific calling convention that gets used when you call functions. So in a normal programming languages, you would have a function call that would have the names of the variables specified. So if the first variable is name, for example, whenever you want to reference that variable, you just call the name of the variable. But then in assembly language, there are no variable names. So there's a specific calling convention that gets used. So RDI would always be the first function parameter. RSI will always be the second function parameter. RDX will always be the third function parameter. So it's important to note that these are only used in the 64-bit architecture. So if you're using a different architecture, the register names will be different. And then another very important register is called the RIP register, the instruction pointer register. This register stores the memory address of the next instruction that gets called in a system. So if you have a function that has different instructions that get executed, the RIP would always store the address of the next instruction. And then you also have the base pointer register, which stores the address of the base pointer, and you also have the stack pointer register, which stores the address of the stack. So that was a 64-bit assembly. This is an example of what a 32-bit assembly program would look like. So on the left-hand side, you will have the instruction, and then on the right-hand side, you have your values and your registers. So for example, if you're adding two values, you would have the add instruction on the left-hand side, and then the registers that you would like, that have values that you would like to add together. And another important thing to note is that whenever you perform an operation in assembly, the answer or the result of the operation always gets stored in the RAX or EAX register, in this case, in the 32-bit processor. Okay, so now that we know what assembly looks like, we take a look at the next important thing, which is the stack. The system stack is what basically stores the structure that the functions will get called in. So right at the bottom of the stack is the buffer, which stores the little information that you'll be getting from the user. And then you get the base pointer, the return function, which is the next function that will get called after the current function. You get the function parameters, and you get the address of the function, the current function itself. So whenever we overwrite the buffer, which is right at the bottom of the stack, we overwrite the next thing, which is the base pointer, and eventually we want to overwrite the return function so that we get control of the next function that gets called after the current function. So now that we know how we can overwrite a function, the next step is knowing how to actually get the program to run what we want it to run. And we do that using shellcode. So shellcode is basically a set of instructions that gets injected and then executed by an exploited program. So it's basically a program that is decompiled into hexadecimal form. So the string at the bottom here, it would be a typical example of shellcode. So if you're interested in more examples, you can go onto the link below. Shellstorm has a very good database of all the different types of shellcode that you could possibly want to use. You can also make your own if you'd like. And now that we know how to actually exploit the program and how to actually get it to run what we want, there are some different tools that can be actually pretty helpful to get the job done. So the first one is the GDB, the General Debugger. For me, it's particularly useful when I'm working with C programs. It allows me to decompile a program. It allows me to follow a program's execution. And I can see the values of the registers at every point of the execution. So whenever I try to overwrite a buffer, I can actually go into the debugger to look at the values of the the registers. And then Little Endian is more of a concept. It is how memory addresses are stored on most systems. So the little bytes come first. So if, for example, you had a 32-bit integer in the hexadecimal format, DEADBEEF, it would be stored as EFBEADDE, which basically, if you look at it, it's from the back to the front. So the simple explanation would be like, since it's stored in a stack format, EF would get pushed to the, DE would get pushed to the stack, AD will get pushed to the stack, BE gets pushed to the stack, and EF gets pushed to the stack. And so when the system tries to read the address, it will obviously pop from the top. So EF will get popped first, and then BE, and so on and so forth. So that's why it reads the addresses from back to front. So the little bytes first. The opposite of little endian is big endian, which does the opposite. And then another important thing is set UID and set GID, which is set user ID and group ID. These are basically file permissions. When they are set, it means you can run a program with using a different user's ID and different users' permissions. So if you don't necessarily have permissions, you can hack a program that has higher or elevated privileges, and you can basically run anything on a file, on a system using the program's permissions. So that's basically the whole goal of exploits like these. And then you might have heard me saying shell a whole bunch of times. So shell is an interactive prompt which we use to run commands. I think most people know bash or sh. It's basically a command prompt. And then another useful thing that I use a lot is NOP or no operation. It's basically, it basically does nothing. So it's particularly useful for exploits like buffer overflows when you have to be precise with your calculations, where you have to calculate the exact memory address where the next instruction will lie. So if you have an NOP calculations, it kind of gives you a leeway where you can kind of estimate where the program will land. And then if it lands on an NOP, it will do nothing until it gets to your interactive shell or your shellcode. So this is useful, for example, if you have a shellcode that is like 32 characters long, and then you most calculate and you land on the third character. Obviously, if you land on a third character of a program, it won't run as it should, so you won't get a successful exploit. So an NOP basically gives you that margin for error. Okay, so now that we've gone through all the theory, we should be able to get hacking. So I'm gonna do an example of how we can put what we just learned into practice. So I have a VM running with a basic C program. In my terminal, I'll just go over what the program looks like and how we can exploit it. That's not it. Cool. So we have over here a program that has a function, call me maybe, which basically just opens a shell, a bash shell, and executes the shell, basically. And then we have in the main function a buffer which has a fixed length of 256. And what happens is there's a scanf that gets data from the user and puts that data into the buffer. But as you can see, there's no validation of the number of characters that the user will be reading. So this is a clearing hole that can be exploited. Theoretically, if we give this program data that is more than 256 characters, it should overwrite the buffer and overflow the buffer. And then once we overflow the buffer, we can basically control the program to do exactly what we want. So the first thing I'm going to show is the permissions. So if we look at the files that are in here, the file that I opened, ch35, which basically is owned by app system 35 cracked, which is not who I am. It's a user account that has elevated privileges. So the goal of this whole thing is to actually get this program to run under that permissions, so we can actually do whatever malicious thing we want to do on the system. So the first thing I'm going to do is I'm going to run it and play around with it and see how it actually works, so I can hack it. In a real world situation, you most probably won't get the source code. So the best way to actually see what the program is doing is to play around with it, and hopefully you can figure out what's going on behind the executable and hack it. So the program gets input from the user and basically just prints it out. So what I'm going to do is I'm going to pipe in a string that is about 255 characters long and see what my program does. So I basically piped in 255 A's into my program, and it worked right. It worked successfully. So that means 255 does not overflow my buffer. But what happens if I put in, let's say, 300 A's? Let's see what happens then. I get a segmentation fault. That basically means I overwrote some data and the program got stuck because it was pointing to something that doesn't exist. So I'm just going to open the debugger so we can actually see what's happening behind the hood. So the GDB is very useful because if I say disassemble, okay. So I'm going to put a breakpoint in my main and then run. So basically, what happens is the disassembler function basically disassembles the executable and shows me the assembly, the representation of the code. So over here, we can see that the data that gets read in gets moved into my RDI. So what I'm going to do is I'm going to try to pipe in the 300 characters to see the data that I'm getting back. Okay. So if you look over here, it's segfaulted. And then if I show my registers, you can see over here the base pointer was overwritten by my A's. So that's not a normal looking address. It's 616161, which is basically all the A's that I put in. So now that we've overflowed the buffer, we can try to overwrite it with a function or an address that we wanted it to run. So if I go back to my if I go back to my code, if we recall, there was a program that actually opens the shell. So what I'm going to do is I'm going to get the memory address of that function and pass it into my exploit, so that that main function actually points to that core memory function and open the shell. So what I'm going to do is I'm going to disassemble the binary executable using object dump so that I can get the memory addresses of all the different symbols that are in the file. So if I do this, it shows me everything that's going on in the executable. This is particularly useful if you don't have the source code and you don't know what to look for. You can disassemble the executable and see everything that's going on. So I have the memory address. So what I'm going to do is I'm going to pipe it in to my program, and then it should overwrite the base pointer and point to my shell function. So before I run that, I'm just going to do a whoami check to see the current user. So once I run that, it should have overwritten the base pointer and pointed to my call me maybe function, and now and open the shell with the new with the different elevated privileges of the new user. So if I run whoami now, it should say app system cracked, which is the user with the elevated privileges. So you can use this to hack many different programs, but I would not advise it. Okay, thank you. That's my that's basically my introduction to buffer overflow exploits.